Section 2.6 is on families of functions. Families of functions are sets of functions in which each function is a transformation or a change from the parent function. The parent function is the simplest form of the function. For example, the functions y equals x squared plus 5, y equals negative 2x squared, and y equals the quantity x minus 4 squared are all transformations of the parent function y equals x squared. A translation is a transformation that shifts the parent function horizontally, that is left or right, or vertically, up or down, without changing its shape. So for a positive constant k and the parent function f of x plus or minus k, so plus or minus outside of the function, is a vertical translation, and that you can see in the box here. So adding k is going to shift it up or down. And for a positive constant h and the parent function f of x, f of the quantity x plus or minus h is a horizontal translation. So in other words, is it on the inside, is going to move it left or right. Now this is a little different. If it's an x minus h, so let's say like an x minus 1, it's going to move it to the right. If it's an x plus 1, it moves it to the left. Your horizontal translations always look a little bit different from what you might think it would be. So here's an example. How are the functions y equals x and y equals x plus 4 related to each other? So the function, do I have my pens here? So the function y equals x plus 4, so it's hard to tell. This is probably one of the most basic functions. So there's not like anything being squared or taken the absolute value of or cubed or anything like that, just y equals x. So this is either a vertical or a horizontal translation. Of the parent function, of the parent function y equals x. So how are these graphs related? So this is actually a translation of y equals x of the parent function y equals x, either 4 units up or 4 units left. And here's why. So I could look at this as y equals just the function x plus 4, okay? And that would be this translation up 4 units, or I could look at this as y equals x plus 4, and that would be the transformation of 4 units left, because that would be the same as y equals x minus a negative 4. So the function y equals x is very basic, so it can be either one. Oops. What is the graph of y equals negative x squared translated down 3 units? So the parent graph of y equals negative x squared is going to be the basic quadratic function, but opening downward. So that's the function y equals negative x squared. And if I translate it down 3, let's go ahead and have some fun with color here, then I would move every point 3 units down. Every point gets moved 3 units down. And it would look like that. And that's going to be the graph of the function y equals negative x squared minus 3. That's a vertical translation, an up or down translation, because it is outside of the function itself. Let's go ahead and let's expand this a little bit. What if I were to take this, and what if I wanted to graph y equals negative x minus 3 squared? Okay, so then that would be the graph of the black parent function moved 3 to the right. So it would be here, and each point translated 3 units to the right. And that's because, so remember, a horizontal translation, left or right, happens within the function. So it's that whole thing that's being squared. Oops. Here's another example. The graph shows the distance f of x you will hike if you leave at 8 a.m. If you leave at 10 a.m., what function represents the transformation? So basically, since 0 is hours after 8 a.m., if I want to leave at 10 a.m., I'm going to be leaving 2 hours after that. Okay, so that's going to be represented by the function f of x minus 2, because what I've done is translated that beginning point 2 units to the right. Remember, that's exactly the same as no, that's actually the same. Okay, and then I would take each of those points and move it 2 to the right, and so my graph would look something like this. And again, that's translated 2 units right. A reflection is a transformation that flips the graph of a function across a line, and generally that line is either the x or the y-axis. Each point of the reflected function is the same distance from the line of reflection as the corresponding point of the original function. So let's take a look at this black function here is f of x. When it's reflected in the y-axis, it flips over the y-axis and becomes this green function here. And you'll notice that the distance each point is from the y-axis stays the same. So this point here, 3, 4, is 3 units from the y-axis, as is the point negative 3, 4. Same thing with the reflection in the x-axis. The black graph gets reflected over the x-axis and becomes the blue graph, and you'll notice each point is the same distance from the x-axis. So for reflection in the y-axis, each y value stays the same and the x value changes sign. The original function f of x becomes f of negative x. And for reflection in the x-axis, each x value stays the same and the y value changes sign. So the original function f of x becomes negative 1 times f of x. So let's take a look at an example here. Let g of x be a reflection of f of x equals 2x minus 7 in the x-axis. What is the function rule for g of x? So since this is a reflection in the x-axis, we're going to use this right here. So g of x is going to become negative that whole function f of x. Or simplifying that, g of x is equal to distributing a negative 1, 2x plus 7. So that would be a reflection of this original line reflected in the x-axis. A vertical stretch multiplies all of the y values of a function by a factor greater than 1. A vertical compression multiplies all y values of a function by a factor between 0 and 1, so like a fraction. So here's a little graph of that. For a function f of x and a constant a, y equals a times the function f of x. It's a vertical stretch when a is greater than 1. So that's going to be the red one here. So it's a vertical stretch, which means that it is further from the x-axis. I'm going to go ahead and write that in here. So it's stretched further from the x-axis, and it's a vertical compression when a is a fraction between 0 and 1, and that's going to be represented by, I think that's the green graph here. There we go, 1 over a, okay? And that's going to be closer to the x-axis because it's a compression. Okay. So the function f of x is shown below. What is the graph of h of x, which takes f of x and multiplies it by 0.5, or 1/2? So a is equal to 0.5, and a is less than 1, and it's actually between 0 and 1, so that means it's going to be a vertical compression, which means it's going to be closer to the x-axis. Okay, so all of my x's are going to be the same, but my y's get multiplied by a 0.5 every time. So I'm going to make a table of values here, and I'm going to do x, y, and then I'm going to have to calculate 0.5 of y. So just picking the points off of the table here, the obvious points that they have here. So I have negative 6 and 3. I have negative 2 and negative 6, 3 and 2, 4 and negative 1, and 5 and 4. So my function h of x, which multiplies every y value times 0.5, is going to give me 1.5, negative 3, 1, negative 0.5, and 2. Now I really ignore this column here, and I'm going to go ahead and graph these ordered pairs. Sometimes if you have a table with multiple columns, it's easier to list the ordered pairs. And 5, 2. And I'm going to go ahead and graph those down here. So I have negative 6, 1.5. And then I have negative 2, negative 3. And I have 3, 1, 4, 1/2, and 5, 2. And if I connect those points and compare it, it's a little hard to see here, compare it to the graph up above, you'll see that it's very similar in shape, but it's just kind of squished closer to the x-axis. Okay, so here's our last example. So last couple examples here. Given the function f of x equals 8x, the graph of g of x is f of x vertically compressed by a factor of 0.5 and reflected in the x-axis. So what is the function rule for g of x? So g of x is going to be a reflection in the x-axis, so that makes it negative, and compression of a factor of 0.5, and then that's going to be multiplied times f of x. So here's my compression, the 0.5, and my reflection is the negative 1. So g of x is going to be negative 0.5 times f of x was 8x, or g of x is equal to negative 4x. And now let's do that the other way around. What transformations change the graph of f of x equals x cubed to g of x equals the quantity x plus 4 cubed minus 1? Well, this in here inside the function means that I'm going to have a translation left 4, and this right here outside of the function means it's going to go down 1. So I have a translation of 4 units left, and 1 unit down of the function f of x equals x cubed. And so in this section we took a look at some of the different transformations that we can do on functions, how you can take a basic plain old parent function and move it up, down, right, left, flip it over the x-axis, flip it over the y-axis, compress it, stretch it, and here's a little box from your textbook that summarizes all of this. I realize this is kind of complicated. We will definitely be doing more of this not only in class but also throughout this course as we approach different functions.